Welcome to Math TV with Professor V. In this video, we're going to go through and review for a Calculus 1 final exam. And how I want to do that is work through the practice final or comprehensive study guide that I give my Calculus 1 class every semester and give you a behind the scenes look at how I create an exam as an instructor, what sort of topics I want to make sure I cover, what sort of skill set I'm looking for when I choose questions for the final exam. And so if you just follow along and work through these problems, it'll help give you a good sense of what areas you probably need to study further, what areas you're pretty good at already, and make sure that you have everything under control before you go take your final so that you can be successful. If you need a review, in-depth lecture, I'll link my playlist of Calculus 1 video lectures, but let's just jump right in. So the first topic that I want to make sure my students have mastered is being able to find limits. And the first type of limits that we found were done without using L'Hopital's rule. So I'll probably specify in the directions, find the limit if it exists, and I might add something like, do not use L'Hopital's rule, because we did that later in the semester. Okay, so let's just start off with something nice. We have the limit as x approaches 5, x squared minus 25 over x squared minus 9x plus 20. So remember, when you're evaluating a limit and x is just approaching a finite number, you want to try to just directly substitute in or basically plug in that number for x. And if you get just a normal constant, you're good. You can just move on with your life. So let's see, 5 squared minus 25 over 5 squared minus 45 plus 20. Yeah, I'm going to get a 0 over 0, which we know is an indeterminate form, but we can't use L'Hopital's rule. So what else can we try? Well, one of the first things you learned was to factor, especially since this is a rational function and it looks pretty factorable in the numerator and denominator. So let's see, x squared minus 25, that's a difference of squares. So we have x minus 5 times x plus 5. And then how's that denominator factor? Can you think of two numbers that multiply to 20 and add to negative 9? Oh, good, look at you, already starting off nicely. X minus 5 times x minus 4. Perfect. So then I can cancel out that common factor of x minus 5, and that should fix things for me. And then notice I'm writing lim every step of the way until I actually evaluate the limit and have a number as my answer, or infinity if it turns out to be infinity or whatnot. Don't forget to write lim every step. Unless, you want -1. Maybe you don't want to intimidate others with your perfect score. Okay, can we use direct substitution now? So 9 plus, my head's going too fast, 5 plus 5 over 5 minus 4, yep, we're good. I don't have to write lim. I already took the limit. There's no more x's in here. So this is 10 over 1, which is 10. Perfect. All right, let's look at another example. Again, no L'Hopital's rule. No. Limit as x approaches 1, x to the 4th minus 1 over x minus 1. Okay, let's see if I just plug in 1. Again, we have 0 over 0. All right, so can you factor the numerator? It's a difference of squares, right? It's x squared plus 1 times x squared minus 1. Oh, but we know better. X squared minus 1 factors further, right? So you don't stop there. No, that's going to factor into x minus 1 times x plus 1. X squared plus 1 does not factor further. It's a sum of squares. Those are notoriously prime. Oh, yeah. Anything you notice? Good. X minus 1 can cancel. And then we should be in good shape. Lim. X approaches 1. X squared plus 1 times x plus 1. Yep, I'm good to go. 1 squared plus 1 times 1 plus 1. That's 2 times 2, which is 4. All right, lovely. Let's look at another. So far, things are starting off fabulously. Don't be intimidated. Oh my goodness. Everyone has a meltdown the minute things get just ever so barely more complicated. Okay, we're looking at the limit as x approaches 2 from the right. I don't care yet that it's from the right unless I run into some situation where I have a constant over 0. Don't be doing wild things like plugging in 2.1 for no reason, okay? Just plug in 2. We're coming from the right. If it's going to be relevant, we'll talk about it later. It's not relevant right now. So can I evaluate this limit if I just plug in 2? Let's see. 2 over 2 plus 2, that's 4. So far I like it. Negative 4 times 2, that's negative 8 plus 4, over 2 squared plus 2 times 2. I mean, this is just 1/2. And then in the numerator over here, negative 8 plus 4, that's negative 4 over 8. That's negative 1/2. So that's just negative 1/4. That's it. That's literally all there was to it. So why did they tell me it was from the right? I don't know, because they felt like writing the problem that way. Was it relevant? No, because we got a non-zero constant. We're good, even if the constant was 0. The only time you'd have to worry about which side it's coming from is if it affected the actual limit because you were approaching maybe infinity or negative infinity and whatnot. So what am I talking about? Don't worry, I got an example for you coming up. Okay, here we have another interesting case. Limit x approaches 0, square root of 1 plus x minus 1 over x. Again, try. If you just substitute in 0 for x, square root of 1 minus 1 over 0, you get 0 over 0. Now, factoring is not such an obvious way to proceed. So what we're going to do instead is multiply by the conjugate of the numerator. Why am I thinking to do that? Because I see a radical, and a lot of the times when there's a radical involved in the limit, it's a good idea to try multiplying by the conjugate. So I'm going to multiply by rad 1 plus x plus 1. So when you're figuring out what the conjugate is, you change the sign right there between the two terms. Don't touch what's underneath the radical. Leave that alone, please. Okay, promise? Good. And then you have to do the same thing in the denominator. Okay, don't forget. You can't just willy-nilly go multiplying by rad 1 plus x plus 1. No, then you're changing things, right? Same thing in the top and bottom. Okay, let's see where we're at now. Limit x approaches 0. The whole point of multiplying by a conjugate is so that you have a difference of squares. So now I have a minus b times a plus b, basically in the numerator, which is going to multiply out to a squared minus b squared, right? Good. So a squared would be rad 1 plus x times rad 1 plus x, which is just 1 plus x. Minus b squared is 1 times 1, which is 1. The denominator, let's leave it factored. I'd say 99% of the time, you don't want to multiply out the denominator. So I default to not distributing, not multiplying out. Okay, notice anything lovely happening? Yes, these ones cancel. Now I have the limit as x approaches 0 of x over x times rad 1 plus x plus 1. These x's cancel again. How fabulous. Now don't forget, that means I will have a 1 in the numerator, right? Can we evaluate this limit? If I just substitute in 0 for x now? Why, yes, look, we have 1 over square root of 1 plus 0 plus 1. So that's 1 over 1 plus 1, 1/2. Beautiful. Wow, wow, wow. So up until now, we've done quite a few limits. I'd probably put something like this on the exam to see if students can remember to multiply by a conjugate. And then maybe I'd put something else where they just have to factor, like the earlier ones that we did. This one's a little basic, but you know, that's always nice to switch it up. Maybe something like this, just to make sure they know how to deal with that kind of 0 over 0 situation without L'Hopital's rule, And also most students are pretty good at these, so I like to give them a problem to boost their confidence when they start the test, you know? Okay, next one, we have the limit as x approaches 6 of x plus 6 over x minus 6 squared. So right off the bat, if you try to substitute in 6, we have 12 over 0 squared. And this is a special case when you have a non-zero constant and the denominator is approaching 0, this quantity approaches either positive or negative infinity. And if you need a review of infinite limits, I'll link a video here. It's pretty stellar, and I just go through a bunch of examples to really help break down this idea for students. Sometimes this limit cannot exist if you're unable to determine whether or not the terms are approaching positive or negative infinity. So let's see what's going on in this case. They didn't tell me from which side we're approaching 6, but I'm actually okay with that because notice the denominator is squared. So what does that tell me? The denominator is always going to be positive, and then the numerator is approaching a positive number, 12. So without a doubt, I can say, okay, this limit, the terms here are going to be positive as x approaches 6, whether it's from the left or from the right. And so I can just say, okay, this limit is going to be positive infinity. And that's really it. That's really all there is to it. Now, I'll just do like a little alternate limit problem. Say instead it was the limit as x approaches 6 of x plus 6 over x minus 6 cubed. So now I can't say, okay, the denominator is always positive because if something is negative and you cube it, it stays negative, right? So then you have to consider two different sides. So you're going to look at the limit as x approaches 6 from the left, and then the limit as x approaches 6 from the right. Okay, so let's see what happens. Now, in this case, yeah, you can think of maybe like 5.9 and 6.1 if it helps you. So as x approaches 6 from the left, yeah, think we're coming from numbers a little bit smaller than 6. The numerator is still going to be positive, right? Say you have 5.9 plus 6. Yep, that's positive. Now the denominator, say you're approaching through numbers ever so barely smaller than 6. So like 5.9 minus 6, that would be negative. And then if you cube a negative number, it stays negative. Yep. So this limit here, positive divided by negative, all the terms here are going to be negative when you're approaching 6 from the left. So what does that mean for us? This limit here is negative infinity. Okay. What if we approach 6 from the right? So you could think of maybe 6.1, yeah? The numerator is going to be positive. The denominator, 6.1 minus 6, that's positive. Cubed is going to stay positive. So if we approach 6 from the right, this limit's going to be positive infinity. Okay. But notice the original problem that I posed was a two-sided limit. Two-sided meaning they didn't tell me if it was from the left or from the right. So notice the limit from the left of 6 is negative infinity, but the limit from the right of 6 is positive infinity. They're not the same. So what does that tell me about the two-sided limit? This limit does not exist. All right. I don't put equals does not exist because it doesn't equal anything. It just does not exist. But like I said, if you need more review, if this topic is something that you struggle with, which is super normal, that's why I made a whole extra video, then just check the description box or rewind a little bit to where I first linked it. Okay, we doing all right? Next, my favorite, absolute value functions. So I always tell my students, when you're in calculus, the minute you see an absolute value function, I want you to turn into a little math robot and then rewrite that absolute value function piecewise, okay? You can write the whole function here as a piecewise function if you want, or you can just write the absolute value portion. It's kind of up to you. Let's do the whole thing. Let's do the whole thing. So let's rewrite this guy piecewise. If you need a review on how to rewrite absolute value functions piecewise, I'll link the video here. Okay, so to determine where to split the domain, you look at where the quantity inside the absolute value equals 0. It's at 11. And I have to be careful because I have 11 minus x in the denominator, so that means x cannot equal 11. It's not in my domain. So I'm going to have one portion for x greater than 11 and one for x less than 11, but neither is going to be inclusive because if x equals 11, the denominator is 0. All right? If x is greater than 11, 11 minus x, this stuff inside the absolute value, is negative. So taking the absolute value would change the sign, right? Take the opposite of that quantity. So without it, I have to write negative 11 minus x over 11 minus x. And then if x is less than 11, then 11 minus x right here is already positive. So taking the absolute value doesn't do anything. So we're just left with 11 minus x over 11 minus x. And we can simplify this, can't we? Why, yes. Bam, bam. That's just negative 1 if x is greater than 11. And then similarly, we just have positive 1 if x is less than 11. All right. So notice they're asking us to find the limit as x approaches 11. They're not telling us from which side. So I need to check both sides because notice that's precisely where the domain splits for my piecewise function. If they asked me for like, this is important, let me explain this. If they asked me for the limit as x approaches 10 of this guy, you don't need to check both sides of 10. You just go, oh, 10 is less than 11, right? So I'm going here, and that limit is 1. That's literally all you need to do, because 10 falls into this portion of the domain. Done. The tricky thing is when they ask you right where the domain splits. So you're like, which one do I use for 11? The left side or the right side? Well, you check both. That's what you got to do. So as x approaches 11, first we're going to check. Let's check from the right. Of absolute value of 11 minus x over, ooh, how ugly, over 11 minus x. So from the right, we're coming from values larger than 11. This limit's negative 1. It's just a constant. And then if we approach 11 from the left, from values smaller than 11, it's equal to 11 from the left, positive 1. Yes. Lovely. So what does that tell me about the two-sided limit? Well, the limit from the left doesn't equal the limit from the right, so this limit doesn't exist. You know, I think it would be helpful if we had a cute little graph, if you're kind of struggling with this idea. Would you be able to graph this piecewise function? This is a pre-calc problem. Can you do it? Domain splits at 11. The function's constant on both sides of 11. So it's just horizontal line. It's positive 1 if x is less than 11, negative 1 if x is greater than 11. Okay, we got it. You know, just to help you see what's going on. Here's x. Here's 11. This is where all the action happens. You don't need to make 11 tick marks. Your graph, your world. Here's 1, negative 1. There's going to be an open circle at 11. It's not in the domain. It's equal, the function equals negative 1 if x is greater than 11. So open circle, boom. Positive 1 if x is less than 11. Okay. Pretend it went through beautifully. Oh, it did. Great. Okay. So then you can see too why other scenarios are not so confusing. If I ask you the limit as x approaches negative 23, absolute value 11 minus x over 11 minus x. And you're like, oh, well, negative 23 is somewhere over here. That limit's going to be 1. So you can answer this question, this limit, definitively, right? With any two-sided limit's going to be fine as long as it's not at 11. That's where you run into problems, okay? The idea is if you tell your friend, hey, meet me at 11, you might not run into each other. Oh, one of you went to 1, one of you went to negative 1. That's the problem. Okay, good. I feel good about it. Now, more ideas for limits. The squeeze theorem. The squeeze theorem or the sandwich theorem tells us that if you have a function and you can bound it between two other functions, so say g of x can be bounded below by f of x and above by h of x, then as long as the limits of the function bounding it below and above are the same, so the limit of f of x is L, say f of x is the lower bounding function, and the limit of h of x is L, then that tells us the limit of g of x must also be L. And then here's a little visual example to help you. Here's h of x, the function bounding g by above. Here's f of x bounding it by below. And if I know h and f have the same limit, well, g is squished in between or squeezed, and it has to have the same limit. All right, when to use the squeeze theorem? A lot of times when you have a trig function like sine or cosine, it's appropriate because you can bound them easily. And, you know, don't just jump straight to squeeze theorem because you see sine and cosine. Just make sure first it's necessary, that you can't just use direct substitution. Okay, so here we have an example. Find the limit as x approaches 0 of x squared times cosine of 1 over x if it exists. So if I try to just directly substitute in x equals 0, here's the problem. X squared is going to 0, fine. 1 over x, where's that going? 1 over 0 is going to approach either positive or negative infinity. And cosine of something approaching positive or negative infinity does not have a limit because cosine oscillates like this. So you basically have 0 times something that does not exist. So that makes us very uncomfortable. And then they're telling us to find the limit if it exists. So now you're entertaining the possibility, maybe it doesn't exist, but no. What we're going to do is start off by bounding cosine, and then the squeeze theorem is going to come into play. So here we go. We know that cosine of theta is always between 1 and negative 1, right? Good. So that means cosine of 1 over x is also always going to be between 1 and negative 1. And I want to make this middle portion of my inequality match the function whose limit I'm trying to find. So I'm trying to find the limit of x squared times cosine of 1 over x. So that's what I want to have right here in the middle, bounded. So I can use the squeeze theorem. I want to squeeze that function. So I'm looking, okay, I got cosine 1 over x, looks lovely. What am I missing? I'm missing an x squared. Can I justify multiplying by x squared throughout this entire inequality? Will the inequality be preserved? Well, x squared is positive, right? So that means it's okay. Well, I guess it could be 0, but we're approaching 0. So I know it's not 0. The only time you have to kind of stress about inequalities is if you multiply or divide by something that's negative. But x squared is positive, so we're good. So I can go ahead and multiply everything through by x squared. So I'm going to have negative 1 times x squared is less than or equal to cosine 1 over x times x squared is less than or equal to positive x squared. So if you look at the setup for the squeeze theorem, then this is basically my g of x, this is my h of x, and this is my f of x. I mean, no one cares though what they're called. Nobody cares, I'm telling you. What do I do from here? I just check that the limit of the function below and above are the same. What if they're not? Then you chose wrong, or you can't use the squeeze theorem. So x is going where? Where is it going? To 0. So let's check now. What's the limit as x approaches 0 of negative x squared? Oh, this is easy breezy. Just plug in 0. It's 0. And let's check what's the limit as x approaches 0 of h of x, positive x squared. 0 again. Ding, ding, ding. So that means the function bounded between them is squeezed or forced to have the same limit. Please summarize nicely. This is the limit that tells us the limit as x approaches 0 of x squared cosine 1 over x also equals 0. Cite your sources. Don't be a plagiarizing little mathematician. By the squeeze theorem. All right. Good. Fabulous. Now, let's look at some more limit problems before we jump into continuity. I know. Determine the limit by sketching an appropriate graph. So they're asking for the limit as x approaches -3 from the right of f of x, where f of x is defined as follows. So -3 from the right, I mean, I don't need to sketch a graph. I could just say from the right side of -3 means I'm coming from values larger than 3. So that's here. So I would just plug in -3. I'm thinking it's going to be -9. But they told us to graph. And a lot of success in math hinges on you just being an obedient little math student, okay? So here we are graphing our little hearts out. That was crooked. I don't like it. Okay. Here's the y-axis. Let's see. All the spice is happening between -3, 0, and 2. So let's scale it nice and spread out there so we can really see what's going on. Up to 2, blah, 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 to -3. Okay. So f of x equals 3x if x is between, greater than or equal to -3 or less than or equal to 0. So if x equals -3, this will be -9. So I'm just going to draw a little tick mark down here and say -9's right there. That's going to get a closed circle because it's inclusive. And then at 0, I'm going to put an open circle. Did you notice this is a strict inequality? Yeah. So we've got a hole right there. Connect all that. Or x is greater than 0, less than or equal to 2. So if x is 2, 3 times 2 is going to be 6. That was 9. I'll just say this is 6. Well, the slope should be the same. So just continue onward. Wow. I can make it just a wee bit better. Lovely. And close circle here. Okay. Perfect. Now, they told me if x is precisely equal to 0, the function equals 3. Okay, a little odd, but whatever. So that means I'm just going to have one little lone closed circle right there. And then everywhere else, if x is less than -3, so over here, or x is greater than 2, the function's just equal to 0. Okay. Open circles, and then 0. Can you see? I'll color it in a little more. It's just equal to 0, and then greater than 2. Okay. I'm coloring a little thick over the axes so you can see it. So the limit as x approaches -3 from the right, that means you're heading towards -3 and you're walking on the graph from the right side. Where are you going? You're going to -9. Like I said, we didn't really need the graph, but it's okay. But since we have this lovely graph, let's just do a few more. So what would the limit be as x approaches -3 from the left? Now you're walking on the graph from here. Hey, look at me. I'm going where? What's the y value that you're approaching? 0. Very good. What is the limit as x approaches 0 from the left? So 0 from the left, you're here. Walking this way, where are you going? You're heading towards 0. What's the limit as x approaches 0 from the right? Same thing, right? You're walking on the graph from the right side. So here's an interesting question. What if I asked you what's the limit as x approaches -3? I'm not saying from which side. And then what's the limit as x approaches 0? I'm not saying from which side. Well, if I'm not saying from which side we're approaching -3, then that limit doesn't exist. Why? Because the limit from the left does not equal the limit from the right. If we're approaching 0 and I'm not telling you from which side, in that case, the limit from the left equals the limit from the right. So I can say the limit is 0. Now you might say, but wait a minute, there's an open circle. There's nothing there at 0. I know, that's okay though. We're talking about limits. No one asked you what's the function equal to at 0. Limits are all about what you're tending towards, what you're approaching, not necessarily what's happening exactly at that value. That's why it's a limit, right? So we don't care that f of 0 is equal to 3. The limit, as you're walking on the graph, it's approaching 0. That's what our answer is. All right. And then this nicely bridges into the next topic that I wanted to talk about, which is continuity. Okay. So remember, there's 3 conditions that have to be satisfied for a function to be continuous at a point x equals a. And they are as follows. First one is that f of a is defined. So the function exists and it is defined as a finite number. Okay, you can't have an asymptote or something there. Second thing, the limit as x approaches a of f of x exists, and that limit needs to exist as a finite number also. And then condition 3 is that the limit of f of x as x approaches a equals f of a. So basically your results from step 1 and 2 are the same. So this limit has to equal the function value from step 1. So oftentimes you'll see that the definition for continuity is combined into a single statement, just the third condition, because in order for the third condition to be satisfied, the first 2 must be true, right? If 1 or 2 fails, then there's no point checking condition 3. Now, this is how to check if a function is continuous at a single point. It can be very tedious and also unnecessary for other functions whose fall into the following categories. So basically, unless you have a piecewise defined function or you're told specifically to apply the definition, most of the time you're not checking conditions 1, 2, and 3. What I'm trying to get at is there's a very crucial theorem that tells us all of these functions are continuous at every single number in their domain, and you're going to utilize this a bunch. So polynomials are continuous on their domain. Their domain is all real numbers, so that means polynomials are continuous on all real numbers. Rational functions are continuous on their domains. Root functions, like square root functions, cube root functions, trig functions, inverse trig functions, exponential functions, logarithmic functions. So you might be saying, that sounds like every single function out there. It's not, but it's quite a few of them. Who doesn't fall into this category here that this theorem applies to? Well, piecewise defined functions. So that's where you're going to run into needing to apply the definition and check conditions 1, 2, and 3. But most of the time, if you're asked to determine whether or not a function is continuous somewhere, you can just cite the theorem if you can identify it appropriately. However, if the directions say use the definition, then you use the definition, you know. So here's an example. Find all points where the function is discontinuous and identify which conditions of continuity fail. So think about it for a minute. If you need to pause the video, that's cool. Give it a try. I'll tell you right now, there's 3 points where the function is not continuous. Okay, so if you want to think back to like a pre-calc definition for continuity, we used to say you could trace the graph with your pencil without having to lift it. And that would tell you that the function was continuous. So just eyeballing, oh, I have to lift my pencil here, so there's obviously a problem. Oh, I have to lift it again here at x equals 0, so there's another problem. And then what in the world is going on at 2? There's another problem. So 3 places at x equals 0, at x equals -2, and at x equals +2. Okay, so let's identify which conditions they mean conditions 1, 2, 3 of continuity fail. So at x equals 0, first condition is that f of a, in this case f of 0, needs to be defined. The function is not defined at x equals 0. I know there's an asymptote there, a vertical asymptote, but you could still define it to be like some random point like we saw earlier. They didn't do that. So f of 0 is not defined. So condition 1 fails. Okay. Second condition, what's the limit as x approaches 0 of f of x? Can you identify that limit? Well, from either side, the function's approaching positive infinity, and that's not a finite number. Remember, for continuity to be satisfied, that limit has to be a finite number. So, nope, not finite. And since condition 1 fails, condition 2 fails, then obviously 3 fails. So wow, at x equals 0, everything's just failing. Such a failure. Okay, what about x equals -2? So what is f of -2? Do we have a function value? No, we have an open circle. Oh my goodness, not defined. Can we figure out what the limit is as x approaches -2? Yeah, actually we can. Look, if you're walking on the graph from the left side of -2 or from the right side, you're going to the same place. You're approaching 2. So that limit is 2. That's finite. That's okay. But you guys, condition 1 failed. That's fail. Fail, fail, fail. So obviously condition 3 fails because 1 failed. Okay. What about x equals +2? So is f of 2 defined? Do we have a function value? Yeah, we do. How strange. Look, f of 2 is equal to 1. I know, it's not like connected to the rest of the graph, but it's defined. You can't be so picky, okay? F of 2 is equal to 1. So yeah, that's okay. That's satisfied. What is the limit as x approaches 2 of f of x? Does that exist? Check from both sides. So from the left side of 2, that's me walking. I'm heading to 2. I tell you to meet me. You're coming from the right side. Are we going to end up at the same y value? Oh, we sure are. We're going to have a jolly good time at y equals 2. Okay, so this limit is 2. Oh, so far we're 2 for 2, guys. Condition 1 passed, condition 2 passed. But condition 3 fails. Why does it fail? Because f of 2 does not equal the limit as x approaches 2 of f of x, right? The function value does not equal what the limit is. So that's why you have that little break in your graph. Okay? Very good. All right, so a very important application of the idea of continuity is the intermediate value theorem, and it states the following. Suppose that f is continuous on the closed interval from a to b, where f of a does not equal f of b. So the function value at the endpoints is different. Let n be any number between f of a and f of b. Then there exists a number c in the interval from a to b, such that f of c equals n. So we can think of the graph of a continuous function as having no holes or breaks, and then just imagine a horizontal line, y equals n, below the higher value and above the lower value of f of a and f of b, so somewhere in the middle. So clearly the line must cross the graph somewhere between these two values. And why this theorem is so important is it helps us identify specifically where zeros of functions live. So a lot of the time we like to let n equal 0 and say that we can find a root or prove the existence of a root between two numbers, and we use the intermediate value theorem to do it. So let's see how this might be put into practice, what you might get asked on an exam. Use the intermediate value theorem to prove that 7 sine x equals x has a solution between pi over 2 and pi. So if I want to use the intermediate value theorem, first and foremost, I need a function. So let's let f of x equal 7 sine x minus x. And we need to make sure we're even allowed to use the intermediate value theorem. We have to make sure its conditions are satisfied. So what were the conditions again? F has to be continuous on the closed interval from a to b, and f of a has to be different than f of b. N has to be between f of a and f of b. So specifically here, these are the values a and b. And if we're trying to find a solution to this equation, that's the same as saying f of x equals 0. So just think in your head, okay, capital N is 0. And all I need to make sure I can show is that f of a and f of b have opposite signs. One has to be positive, one has to be negative. Then for sure 0 is going to be between them. And then I can prove that f has a solution. or a 0. Now, I have to make sure f is continuous on the interval from a to b, but I'm just going to use that theorem. I don't need to check conditions 1, 2, and 3. So f of x is a combination of a trig function, right, 7 sine x, and a polynomial. That's what that negative x is. What's the domain of f of x? Well, sine of x, that domain is all real numbers. X is a polynomial, domain is all real numbers. So that means the domain of f is all real numbers. And we know that f is a continuous function on its domain. So f must be continuous on all real numbers. Therefore, f is obviously going to be continuous on the subset, the little interval from pi over 2 to pi. So we can use the intermediate value theorem. If you don't state this, I would take points off, okay? You can't just willy-nilly use the intermediate value theorem without verifying that it's appropriate. Now we have to check what f of a and f of b are. So f of pi over 2 and f of pi. So 7 times sine of pi over 2, that's 7 times 1 minus pi over 2. Well, I know 7 is bigger than pi over 2, so this is positive. And then f of pi would be 7 times sine of pi is 0 minus pi. So we have 0 minus pi, which is less than 0. So if n is 0, n is for sure less than f of pi over 2 and greater than f of pi. Therefore, by the intermediate value theorem, there exists, look at this snazzy math abbreviation for there exists, a number c on the interval from pi over 2 to pi such that f of c equals 0, which means 7 sine c minus c equals 0, which means 7 sine c equals c. So a solution to the equation can be found between pi over 2 and pi. Voila. Okay, how was that? Make sure you can really understand the theorem. That way when you write up the solution, you're not missing any parts, right? Otherwise, it's just going to feel like memorizing a bunch of weird steps. But if you understand what needs to be said, then it really helps everything kind of come together. Okay, I might be in the mood to put something like that on my final. Now we're going to go into limits as x approaches infinity or negative infinity. And again, no L'Hopital's rule, okay? So x is approaching negative infinity. When you're trying to evaluate these limits, look at the highest power in the numerator and denominator, because that's going to control basically where each of them is headed. X going to negative infinity means the numerator is going to go to negative infinity. X cubed is running the show upstairs. And then in the denominator, x squared is running the show, but there's a minus in front of it, so that's also going to negative infinity. So we do have an indeterminate form of the type infinity over infinity. But I just told you no L'Hopital's rule. So what do? Cry into your paper? No. We divide by the highest power of x from the denominator. So I'm going to divide by x squared. If you want to think of it as multiplying by 1 over x squared, if that helps you, go for it. Okay. So this is the limit as x approaches negative infinity. I'll write it out gently step by step, okay? 4x cubed over x squared plus 3x squared over x squared over x squared minus 6x squared over x squared. Okay, I usually would not write that step out. I would just start simplifying already. Okay, this just... But if you're just getting back into the swing of things, it's all right. So we'll have 4x plus 3 in the numerator, and then 1 over x minus 6 in the denominator. So let's think here. X is going to negative infinity. So 4 times negative infinity, that's still going to negative infinity, people. If I add 3, is anything going to change? No, it's still going to negative infinity. What's going on in the denominator? So 1 over x, 1 divided by something getting really, really big, even if it's negative, that goes to 0. So we have 0 minus 6. So we basically have negative infinity over negative 6. What does that mean? Well, the two negatives will cancel out. If you take something that's approaching infinity and divide it by 6, you guys, it's still going to infinity. So this limit's going to be positive infinity. Positive because the two negatives cancel out. Bam, bam. But it's still getting very, very large. Okay? Oh, good. That was such fun. Let's try another. Keep the party going. Limit as x goes to negative infinity again. I'm not a negative person. I'm just in the mood for negative infinity. And then we've got cube root of x minus 6x minus 4 over negative 7x plus x to the 2/3 plus 4. Quick check. Highest power in the numerator is x to the first. Same thing here. And both are going to be going to negative infinity. So I'm just going to start off dividing by the highest power of x in the denominator, which is x to the first. So same as multiplying by 1 over x. Okay, good. Let's see if you can simplify this one on your own. So limit x goes to negative infinity. Why don't you pause the video, distribute 1 over x through, and simplify, okay? Good. How'd you do? So you've got, for this first term, cube root of x is x to the 1/3 over x to the first. That's going to be 1 over x to the 2/3. Subtract the exponents. Wherever it's higher, wherever the exponent's higher, that's where you're going to have them left over. Minus 6 minus 4 over x over negative 7 plus 1 over x to the 1/3 plus 4 over x. Is that what you got? Oh, great. So x is going to negative infinity. 1 over x to the 2/3 goes to 0. Negative 6 is a constant. It's just hanging out at negative 6. Minus 4 over x goes to 0. Negative 7 is also a constant. 1 over x to the 1/3, that goes to 0. 4 over x goes to 0. So all we have here is negative 6 over negative 7, which is 6 over 7. Woo! Good. You feeling like you're getting the hang of these? Lovely. Now, what about this one? Limit x goes to negative infinity, cosine 5x over x. So if x goes to negative infinity, where's cosine 5x going? Cosine's graph looks like this. Not exactly, but you get the idea. As x goes to negative infinity, we're going this way, it's just oscillating. So that limit doesn't exist. And then x is going to negative infinity, so the denominator is going to negative infinity. How strange. What do? I can't divide by x. That won't help things. Maybe it's time for the squeeze theorem. I'm serious. Okay. So remember, we just did this earlier. We know cosine of some angle is always between 1 and negative 1. So that means cosine of 5x is also between 1 and negative 1. I want to make this function that's bounded in the middle match the function that I'm trying to find the limit of. So all that looks like is going on is I'm missing an x. I need to divide by x. But I have to be careful. Since x is going to negative infinity, that means x is less than 0, right? So I'm going to go ahead and divide everybody by x. But I'm ever the precise mathematician. That means the direction of my inequalities need to get reversed. When you multiply or divide an inequality through by a negative quantity, the signs flip. The direction of the inequality flips. Okay. It's fine though. It really won't affect too much of the result. It's just something that shows that you're being a precise mathematician, okay? So hold yourself to that high standard. Now let's check. What's the limit as x goes to negative infinity of negative 1 over x? Denominator's getting really, really big. I don't care. There's a constant in the top. That's going to 0. Also, the limit as x goes to negative infinity of 1 over x, that's going to 0 also. Therefore, by the squeeze theorem, Let's rewrite the original limit, like angelic little calculus students. The limit as x approaches negative infinity of cosine 5x over x equals 0 also. Boom. A plus. So far I'm doing A plus work. Are you? Yeah. Don't cut corners, you know? It's your test. Think of it like you're on trial and the jury's going to decide your grade. So you want to show an abundance of evidence that you deserve an A. A students don't cut corners, or even if they could, the jury won't know that you actually know what you're talking about. So show them all the evidence, give them all the proof that you know what you're doing. Okay, here's another cute one. Limit as t approaches infinity of square root of 4t squared minus 8 over t minus 2. So numerator is going to infinity, denominator is going to infinity. We're going to divide by the highest power of t from the denominator. In this case, it's just going to be t to the first. So I'm going to multiply top and bottom by 1 over t. So let's see what we got going on now. So we have the limit as t approaches infinity. Now be careful here. When you put 1 over t underneath the radical sign, it becomes 1 over t squared. I'll link a video here where I talk about that in more depth. And then we have 4t squared minus 8 over 1 minus 2 over t. Okay? Now you do have to be careful sometimes. In this case, t is going to positive infinity. So square root of 4t squared, that's going to be absolute value of 2t. Sometimes when you simplify, which is going to be positive because we're going to positive infinity. But if you need a little more clarification on some of the nuances, I'll link a video here where I talk about it. Okay. So let's distribute the 1 over t squared through underneath the radical. So limit t goes to infinity. I have radical 4 minus 8 over t squared over 1 minus 2 over t, and then 8 over t squared, that's going to go to 0. 2 over t, that goes to 0. So I just have square root of 4 over 1, which is 2. Oh, that was harmless, right? Yes, harmless indeed. Okay. Ooh, here's a cute one. Limit as x approaches 5 from the right. So numerator is just a constant. Denominator, 5 squared minus 25, that's 0. So non-zero constant over 0, it's not an indeterminate form. It's either going to be positive infinity, negative infinity, or it doesn't exist. If we're approaching 5 from the right, that tells me something though. X is a wee bit bigger than 5, like 5.1, 5.01. If I square it, it's going to be a wee bit bigger than 25. So when I subtract 25, yeah, the denominator is approaching 0, but through positive values. So this whole quantity is positive. That tells me this limit is going to be positive infinity. You know, I think students hate these because there's not a lot of steps to write out. You just have to stop and think about it, and that can be dangerous. I know, but you can do it. All right, building on that idea, here's another. The spice factor on this one is intense. This is like Serrano level limit. Okay, x approaches 1 from the right. Try direct substitution. So 1 over 1 to the 4/5 minus 1 over, this is 1 minus 1, so that's 0 to the 2/5. What in the world? This is just me doing some scratch work. 1 raised to any power, as long as it's finite, is 1. So 1 divided by 1, this is just 1. 0 to the 2/5. Oh, great. Okay, so we've got a non-zero constant over 0. Here's the important thing, though. We're approaching 1 from the right, so values a little bit bigger than 1. Something bigger than 1 minus 1, that's going to be positive. I raise it to the 2/5 power, so you could think of it either way. You take the 5th root, then you square it, or you square it, take the 5th root. It's going to be positive. So this is approaching 0, but through positive values. So that means this whole second term right here is approaching positive infinity. So now I have 1 minus positive infinity. The 1's not going to do much. Minus infinity is running the show. So this limit is negative infinity. Yeah, another frightening limit. Marinate on that one. Okay, here's another lovely one. We have the limit as x approaches infinity of the square root of x squared minus 18x, plus 18x, excuse me, minus x. So let's see, as x goes to infinity, everything here in this first term is approaching infinity, minus, x is also going to infinity. Why did I say uh-oh? Because infinity minus infinity is an indeterminate form. It's not 0. They don't cancel out. If this limit had been changed and there was a plus, then it would just be positive infinity, because infinity plus infinity goes to positive infinity. But infinity minus infinity, no. You basically don't know which infinity is running the show. They're not all infinities grow at the same rate. So if this first one's dominating, the limit could be positive infinity. If this one's dominating, it might be negative infinity. I mean, it could be 0, or it could just be some other constant. There's so many options. I can't determine it. That means it's indeterminate. Okay. So there's a radical. What did we do last time we saw a radical? We divided by the highest power of x in the denominator. I don't have a denominator. Let's make one. How do I make one? Did we do something else with radicals earlier in this review? Yeah, we multiplied by a conjugate. That seems like the way to go. So I'm going to multiply by the conjugate, but I have to do so in the top and bottom, and then I'll have a denominator, and I feel like I can just kind of duplicate what we did a couple examples ago. So I'm multiplying by rad x squared plus 18x plus x, top and bottom. And now let's see what happens. So we've got the limit, x approaches infinity. Here in the numerator, I'm just going to have x squared plus 18x minus x squared. And then in the denominator, we have rad x squared plus 18x plus x. Okay, great. So these x squareds cancel out. And then now I want to divide top and bottom by the highest power of x in the denominator. This is where you need to be careful. I gave you a little warning earlier. The highest power of x is the square root of x squared from the bottom, which simplifies to not x. No, it simplifies to absolute value of x, which, remember, we're in calculus. We think of it as a piecewise function. It equals x if x is greater than or equal to 0. It equals negative x if x is less than 0. So we have to decide which part of the piecewise function is appropriate for us to use in this limit, because I'm not going to keep absolute values throughout the whole limit. That's going to be too cumbersome. Notice x is going to positive infinity, so we're over here. So when I simplify and I'm going to divide by 1 over square root of x squared, which is 1 over absolute value of x, right? I'm basically multiplying by 1 over x, not negative x, which is good. If we had the limit as x approaches negative infinity, and then you were living in this part of the piecewise function, the only difference would be you would just need to add a big minus sign outside the whole thing, and then you would divide by x like I'm going to do right now. Okay, so just pay attention to where the limit's going, and that'll let you know whether or not you need to add an extra negative or not. Okay, so in this case, we lucked out. We're just going to positive infinity. If I was a student, though, taking the test, I would still write this out to show my instructor I thought about it and I wasn't just careless and didn't put the negative. I'm aware of all the, little nuances that are there when taking limits. Okay, if you want to write 1 over absolute value of x, you can do that, or just 1 over x is fine too. I'll distribute it right now. So we've got limit, x goes to infinity, 18x over x, I'll just write it like that. And then remember, when you put 1 over x under the radical, it becomes 1 over x squared times x squared plus 18x plus x over x. Are we good? Okay, so then now we have the limit. X approaches infinity. In the numerator, we're just going to have 18. And then in the denominator, we'll have square root 1 plus 18 over x plus 1. Okay, so let's see. As x approaches infinity, 18 over x is going to go to 0. And then all we're left with here is 18 over square root of 1 plus 0. So that's 1 plus 1, 18 over 2, which is 9. Very good. How'd you like that one? I've put it on my final exam multiple times because it just tests quite a few concepts in one problem, which is nice. I don't like to have very lengthy exams. That's my style. If your instructor likes longer exams, then they probably will put like less complicated problems. I do fewer, more tricky. Okay, limit as x approaches 0 of x squared minus 2x plus sine x over x. To evaluate this limit, we need to recall the fact that the limit as theta approaches 0 of sine theta over theta equals 1. And actually, so does the limit as theta approaches 0 of theta over sine theta. Okay, again, we're not going to use L'Hopital's rule here. So what I'm going to do is actually split up the denominator. So split the x under each of the terms in the numerator and see if that helps me out. I did a quick mental check. We have 0 over 0. So if you're allowed to use L'Hopital's rule, go for it, but we're not. So now we have here the limit as x approaches 0 of x minus 2 plus sine x over x. Oh, okay, so look. So x is going to 0, this is going to 0. Negative 2 is a constant. And sine x over x is going where? To 1. Yes, fabulous. So what am I left with? I have 0 minus 2 plus 1, which is negative 1. Beautiful. I love it. Did you love it? Okay, I'm so glad. What if things don't work out so beautifully? It happens sometimes. Here's a fabulous problem. I like this one. Find a value of c that will make the following piecewise function continuous at x equals 0. Oh my God, we're talking about continuity again? We sure are. So remember, we have 3 conditions for continuity at a specific point. The first one is that f of a, in this case f of 0, is defined. Is f of 0 defined? Well, we have to define it. F of 0 is equal to c. So f of 0 equals c. We need to find it. Okay, second thing is the limit as x approaches 0 of f of x exists as a finite number. When we're working with a piecewise function and you're trying to find the limit, remember, we don't care what the function actually equals at that value. Like as we're looking as x approaches 0, I don't care what the function equals at 0. I care what the graph is tending towards as we approach 0 from both sides. Think of that problem that we did earlier where we had to identify where the graph was discontinuous and which conditions of continuity failed. So if you think back to this problem, notice here, when we were trying to find the limit as x approaches 2, I looked at where the graph was going from one side of 2, the other side of 2. I didn't care what it equaled at 2, okay? So when you're finding the limit and you have a piecewise function, you're looking at where it's tending towards from both sides, but it's not of interest what it actually equals at that point. So going back to where we're at, look at how much we've done. Going back to where we're at, when I'm trying to find this limit, I'm just going to focus on this portion of the piecewise function. Okay, so let's see, does that limit exist? What is the limit as x approaches 0 of sine squared 4x over x squared? Well, there's a reason we just did that limit earlier. where we have the limit as theta approaches 0 of sine theta over theta equaling 1. Yeah. I want you to see how you can use that here. So this is the limit as x approaches 0. Let's rewrite this as sine of 4x over x squared, okay? And you're like, oh my God, we're so close. We are so close. The only problem is whatever the argument is for sine, it has to match the quantity in the denominator. So the argument for sine here is 4x. Man alive, I wish that was a 4x. But here's my motto. When you do math, you don't sit around and just feel sorry for yourself. Like, oh man, I wish there was a 4 down there. You make things happen, okay? You are a problem solver. You go, I'm gonna put a 4 there. I certainly am. Okay. I really added an extra 16 in the denominator, did I not? Because that's a 4 down there squared. If I just multiplied by 1 over 16, I need to multiply by 16 over 1. That way I'm just multiplying by 1, not doing anything illegal. The math police won't come for me. I think we're done, people. We're in business. So this is going to go to 1 squared times 16. So this limit is just 16. Cool. So we found step 2 for verifying continuity at a point. The limit of the function f of x, it does exist as x approaches 0, and that limit is 16. So what's the third condition for continuity? That the function value needs to equal whatever the limit is. And since the limit is 16, then the function value f of 0 needs to be 16 also. And what they asked us to do was find a value of c that will make the function continuous at 0. So choose c to equal 16. So the problem boiled down to just finding the limit as x approaches 0. Okay, that's a great one because it tests if you know continuity, if you understand how to take this type of limit, all sorts of good stuff. Okay, let's get into differentiation rules. I'm not going to do boring little polynomials and easy stuff. We're just going to review some chain rule, product rule, quotient rule, and all that good stuff. If you need a refresher on those rules, like some more basic examples, I'll link some videos here. Okay, find the derivative. So it's quotient rule time. S prime of t, I always sing the song low-d high minus high-d low over low-low. So low means just the denominator. D high means multiply by the derivative of the numerator. Derivative of 2e to the t is 2e to the t. Minus high. D low is derivative of the denominator. That's 2e to the t. And then over low low, so that's 2e to the t plus 1 squared. Square the denominator. All right, looks good. I really encourage you, instead of just jumping straight to multiplying everything out in the numerator, always think of factoring out the GCF. So we have 2e to the t that I could take out, and then I'm left with 2e to the t plus 1 minus another 2e to the t. This will serve you well later on when you have more complicated results from the quotient rule. Okay, just get in this habit now. Don't just FOIL on default or distribute on default. Factor on default. I want to change the way you're kind of programmed. Oh, and then so nicely these 2e to the t's cancel out. And then I'm just left with 2e to the t in the numerator times 1 over 2e to the t plus 1 squared. How beautiful. How truly beautiful. Look at us, quotient rule masters. Okay, here's a product rule time. So z equals 2x squared times e to the x. So we have to do product rule because we have a product of two functions, f times g. So you could say dz dx, oops, or z prime of x, whatever. The product rule, you don't have to be so picky about the order, because remember, it just involves multiplication and addition, both of which are commutative. So just, I like to think of it as take turns. Each function has to take their turn taking the derivative, one at a time. So let's say it's f's turn. Okay, cool. Derivative of 2x squared is 4x times e to the x. It's not g's turn, leave it alone. Plus, okay, f already had his turn, so leave him alone. And then derivative of g, now it's g's turn. How exciting, e to the x. That's it. I mean, you can leave it like that. You can factor out e to the x if you want, and then you have 4x plus 2x squared. And then you might say, ooh, I can take out a 2x as well. So 2x e to the x times, I'll be left with just 2 plus x. I think that's a nice place to take it. That way, if you need to find the zeros, you're ready to go, you know? Don't worry, we'll do more complicated derivatives in a hot second. Here's a good application. So suppose u and v are differentiable functions of x. Use the given values of the functions and their derivatives to find the value of the indicated derivative. I'm gonna read through all this info that they gave me later. I'm differentiating with respect to x, v over u. So this is just a test of, do I know the quotient rule? Yep. So d dx of v over u, let's write it out. We have low u, d high v prime, minus high d low over low low. Those are all functions of x. So really you have u of x, v prime of x, minus v of x, u prime of x, over u prime of x squared. And now they're asking me to find this derivative at x equals 2. So we're evaluating this at x equals 2. We are evaluating this at x equals 2. So what does that mean? I need u of 2 times v prime of 2 minus v of 2, u prime of 2 over u prime of 2 squared. Oh, and they gave me everything I need up here. How lovely. Okay, so just plug it in and go, because we don't have the functions v and u. It's all good. In fact, I prefer this. Isn't this easier? U of 2 is 6. V prime of 2 is negative 5. Let me use parentheses instead since we've got negatives. Yes, yes. Minus v of 2, what is it? Negative 1. And u prime of 2 is 2. Over u prime of 2 squared. Why did I write a prime? It should just be u. Excusez-moi. So u of 2 is 6 squared. Okay, so this is going to be negative 30 plus 2 over 36. So that's negative 28 over 36. I can divide by 4, can't I? Negative 7 over 9. Very good. Were you all screaming at me that I put an extra prime in the denominator? I'm sorry. I didn't mean to give you a fright. Okay. Okay, oftentimes you'll be asked to do something like this. Find the equation of the tangent line with certain conditions. Here it says find all points x, y on the graph of y equals x over x minus 3 with tangent lines perpendicular to the line y equals 3x minus 2. So what they're telling me is that the slope of the tangent line needs to be perpendicular to this line that's given here. Well, what's the slope of this line? The slope is 3. So the slope of a line that's perpendicular to it would be the opposite reciprocal. It would be negative 1/3. Okay, so really what they're saying is find all points on this curve, y equals x over x minus 3, where the slope of the tangent line equals negative 1/3. Well, we're in calculus. How do we find slopes of tangent lines? From the derivative. So m tan is equal to dy dx. So now I need the derivative of this function. And I need to use the quotient rule to differentiate. So here we go. We've got low d high. Derivative of the numerator is just 1. Minus high d low is just 1. Over low low. There's a remix that says square the bottom, away you go. I don't know how you feel about that. Okay, let's clean this guy up. So we have x minus 3 minus x over x minus 3 squared. So that's just negative 3 over x minus 3 squared. So this gives me the slope of the tangent line at any point to the curve x over x minus 3. Well, I want to know specifically, where is this equal to negative 1/3, right? So I'm going to set my derivative equal to negative 1/3. You can cross multiply to solve, right? You remember cross multiplying back in the day? Ugh, if only we appreciated it when that was all we did. So 9 equals x minus 3 squared. Use that square root property. Take the square root of both sides. Just don't forget your plus or minus here. I'll rewrite it like this. X minus 3 equals plus or minus 3. So that means x equals 3 plus or minus 3. 3 plus 3 is 6. 3 minus 3 is 0. Are we done? No. They wanted all points, x comma y. Oh, so demanding. So these are the x values where the slope of the tangent line is negative 1/3. They want the y values on the graph, on the curve, that correspond. So here's the curve. That's where you're going to plug in these x values to get the y values that go with them, to get their little partners in crime. So 6 comma, can you do it in your head? You're in calc now. That would be 6 over 3, so 2. And then 0, that's easy, 0. These are the points. Beautiful. Okay, I told you I got some spicier derivatives for you. Running low on power, so we might have to call it after this. Okay, find the derivative of the function. I'm going to use the chain rule. Okay, so h prime of x is equal to, bring the exponent down in front, subtract 1, leave what's inside alone. Then I'm going to multiply by the derivative of what's inside. In order to do that, I need to use the quotient rule. So here we go. Why don't you pause the video, give it a try. Okay, did you do it? Let's check. Low, d high, derivative of cosine x is negative sine x, minus high, d low is just going to be cosine x over low low. Okay, clean this up. So 4 times, I'm going to distribute the exponent, cosine cubed x over 1 plus sine x cubed. And then let's see what's going on in these parentheses. Doo-doom, doo-doom, doo-doom. Why am I distributing? Because there was nothing I could factor out. I know. Negative sine x minus sine squared x minus cosine squared x over 1 plus sine x squared. So what I'm going to do, I'm going to take this negative outside here, and now everything's positive. Does this look familiar to you? What is sine squared x plus cosine squared x? It's 1, isn't it? That's a Pythagorean identity. So now we have negative 4 cosine cubed x over 1 plus sine of x cubed times, look at this, this is sine of x plus 1 over 1 plus sine of x, which is the same quantity, squared. So we can just cancel both these. One factor of sine of x plus 1. And notice this is 1 plus sine x. This is 1 plus sine x cubed. Let's combine those, and then I think we're done. Negative 4 cosine cubed x over 1 plus sine of x all to the 4th. Beautiful. Wow, I love it. Okay, I'll just end part 1 right here. I was going to do some implicit differentiation and then some related rates, some logarithmic differentiation. I'm going to take you through the whole semester of Calc 1, but we need to charge the iPad. So if you need to do any reviewing, I have the playlist for my Calculus 1 video lectures linked more in depth, so identify which topics you need more help with and If you need review on older math classes like pre-calc, trig, I also have playlists for those classes. So stay tuned. Part 2 will be coming shortly. Keep up the good work, you guys. If you're finding this video entertaining, helpful, all of the above, give it a thumbs up. Subscribe if you haven't already. You can catch me on TikTok and Instagram also at Math TV with Professor V. I'll talk to you guys soon. Bye.